Good day to you all. I am C.S. Srinivasarao, Associate Professor, SVKP and Dr. K.S. Raja Arts and Science College, Penugonda. Welcome back to directed graph. A directed graph G is also called digraph. Consists of two things. One is the set of vertices; those are called nodes or the points. And another set is set of ordered pairs. Ordered pairs is UV of vertices is called arcs or directed edge. So one is the set of vertices, the second one is the set of arcs or the directed edges or simply edges. Suppose u comma v is a directed edge in a digraph, then the following terminology. One is E is the edge, begins at u, vertex u and ends at vertex v. E is an edge that begins at vertex u and ends at vertex v, where u is the origin or initial point of edge E and v is the destination or terminal point of edge E. V is a successor of u, or u is adjacent to v and v is adjacent from u. If u is equal to v, then E is called a loop. So u is equal to v means starting and ending both points for the particular edge E is called a loop. A directed graph v comma E is said to be finite if set of v vertices and set of E edges are finite. Both set of vertices v is finite and set of edges E is also finite. Then that directed graph is called finite directed graph. Now the next one is degrees. Out degree and in degree. Out degree of a vertex v of graph G written as OUT DEZ of v. Out degree is the number of edges beginning at v, starting at v. So for example, if you take the A is the one vertex in this directed graph. This is the directed graph. A is the one vertex. Out degree means from A to some other the remaining vertices. From the source is the A. So only one edge, that is called E1. So the out degree of A is 1. And now in degree. The in degree of V written as INDEZ of V. This is the in degree. Is the number of edges ending at V. Take the same example. What is the in degree of A? In degree of A is equal to incoming edges to the vertex V. One is the E2 and second one is the E3. These two edges are incoming. So ended at the vertex A. The in degree of A is 2. So that is the in degree and out degree. Out degree means from that vertex. In degree means to that vertex. So the sum of the out degrees of the vertices of a graph G is equal to the sum of in degrees. Sum of out degrees is equal to sum of in degrees. So for example, this is the A. Out degree of A is 1. Out degree of B. B means outgoing edge. Outgoing edge is 1 and 2. E4 and E6. That is the out degree of D is 2. Out degree of D is 2. Out degree of B. This is the B vertex. So how many out degrees? Out degree means from that. One is the E2, second one is the E3, and third one is the E5, and fourth one is E1 also. So this is the out degree of B is equal to 4. E1, E2, E3, E5. Now out degree of C is equal to 0. For C there is no outgoing edge. So that's why the out degree of C is 0. In degree of A is equal to 2. Incoming edges to the A. This is E2 and E3. In degree of A is 2. In degree of B B means this is E4 is 1 and E1 is also 1. So there are in degree of B is 2. One is from E4. Second one is from E7. This is not E1. This is E7. Right. E4 and E7. In degree of B is 2. In degree of C is 2. Again, one is E6. This is E5. In degree of C is 2. In degree of D is, here this is in degree. In degree of D is from A. That is the E1 is the even end point is D. So in degree of D is 1. Sum of out degrees is equal to 1 plus 4, 5 plus 0 plus 2, 7. Now is equal to in degree. Sum of in degrees. 2 plus 2, 4. 4 plus 2, 6. 6 plus 1, 7. So both are the same. A vertex V with 0 in degree is called source and a vertex V with 0 out degree is called sink. Right. And this is the directed graph with weights of. Is the weights. Directed path. A directed path P in G is an altering sequence of vertices and directed edges. These are the directed edges. E1, E2, E3 up to En. These are the directed edges. The path P is equal to starting point V0. From V0 to V1, there is a one directed edge that is called E1. For E1, the starting vertex is V0 and ending is V1. For E2, starting vertex is starting means started at E2 started at V1 and ended at V2. Like that. So this is from V0 to Vn. So n plus 1 vertices, n number of edges. N number of edges. The length of the path is n. It means number of edges. It's a number of edges. Length of the path is equal to number of edges. This is the length is n. A simple path is a path with distinct vertices. For simple path, vertices are distinct, means no repeating. And a trail is a path. Trail is nothing but path. So with distinct edges, edges will not repeat. A closed path has the same first and last vertices. A closed path has first and last vertices are the same. Spanning path contains all the vertices of G. So in the simple path, there is a path from one vertex to another vertex. This is a spanning path contains all the vertices of G, a graph G. A cycle or a circuit is a closed path with distinct vertices except the first and last. That is called cycle or the circuit. Now, directed cycle free graph. Directed cycle free or acyclic. A graph S which cannot have any cycles. There is no cycles. That is said to be cycle free or acyclic graph. A directed acyclic graph, that is cycle free graph, is called DAG. For short, you call it DAG. So DAG means directed acyclic graph. So this is the process the vertices one after the other, so that the vertex U is always processed before the vertex V. Whenever U comma V is an edge. So this is a pair of this vertices is an edge. For this edge, U is the starting vertex and V is the ending vertex for the edge for this particular edge. You must process first U and then V. Such a linear ordering T of a vertices S, which may not be unique, that may not be unique. This is called topological order. For example, if you take this is the one directed graph, this is adjacent list. For A, what is the adjacent list? C. This is a directed graph from A to C. For B, there is a D. This is D and F. For C, you take C. So there is no path from C. So that's why this is a nil. For D, you take C. Adjacent is C. For D is over. And E, from this is an edge from E to C. So that's why adjacent for this E is C. For F, just you take F. There is no path from F. Path from F. That's why this is empty. G, from G to A is 1. So adjacent is A. And from G to F, adjacent is F. For G, there are two adjacents. One is the A and second one is the F. So this is the directed graph. So that's why don't consider the other reverse direction. Only in the arrow direction. For A, only C. Right? So this is about the directed cyclic graph and adjacency list. Now topological order. First you go for the topological order. So here the main idea of algorithm is that any vertex n, that is the node n with 0 in degree. 0 in degree means that is the only out degree. There is no incoming edge for the particular vertex n. The algorithm essentially repeats the following two steps. One is find a vertex with 0 in degree. First you find the 0 in degree vertices and delete n. So delete the particular node and its edges from the graph. And the destination vertices in degrees may be changed. That is the topological order. So for this algorithm, first there are several steps. The first step is find the in degree of each and every vertex n of the graph S. So from this graph, find each and every vertex in degrees and insert into Q all vertices with 0 degrees. first you take the data structure Q. So insert all vertices with 0 degree. Repeats the 4 and 5 until the Q is empty. So first from the Q, remove one front vertex from that Q and identify the neighbors of the particular removed vertex, and in degree of the particular neighbors is always the destination from that. So in degree of that particular vertex is equal to in degree of -1, and because this deletes the energy from n to m, and in degree of m is equal to 0 because you are add m to Q. So in degree of, if in degree of the particular node m is 0, then add that m to Q. So whenever the in degree is 0, then you should add the particular vertex to the Q. So repeat this step 4 and 5 until the Q is empty. So this is the topological order. So just you take the same diagram here. This is the adjacency list. Now what are the in degree values are 0. For A, in degree value is not 0. So in degree values are 0 for B, E, G. B for this in degree is 0 because there is no incoming edge for this B. And the second one is E. For this there is no incoming edge for this E. And the third one is G. There is no incoming edge. Just you find in degrees 0 vertices. One is B, E, G ordered. This is B, E, G. So just you place this, add this particular B into the Q, E and G. So front, this is the Q. At front the B vertex, next E and then G. Just you consider the vertex B, consider this vertex B, and this is the one sorted ordered B, vertex B, and then you remove these two outgoing edges from this B. These two outgoing edges. If you remove these two outgoing edges, what is the in degree of D? In degree of D is previously this is 1. Now the in degree is 0. So in degree of D is 0 because you removed this edge. The in degree is previously 1. If you remove this edge, the in degree of D is 0. Now in the previously the in degree of F is 2. If you remove this edge, the in degree of F is 1. Now whenever you remove these two edges, the B is the vertex. Just you remove from the Q, the B is removed from the Q, and only vertices in the Q is G and E. Now again you calculate the in degree 0 vertices. This is the in degree 0 vertex. Then you insert this particular D into the Q. So now the Q, it contains the D. G is already there. B, if you remove this, only two elements are there. So two vertices G, those G, and a newly vertex is D. Newly vertex with in degree is 0. Now again you remove the vertex E from the Q. So that is the you consider the E. This is the topological order, vertex B and then E. If you remove the E, this is the E. And what are the updations? If you remove this edge, so from that E, the remaining vertices, only this one. So remove this edge also. Whenever you remove this edge, the in degree, previously the in degree of C is 3. Now the in degree of C is 2. If you remove this, in degree of C is 2. So no modification or no updations in the in degree of other remaining vertices. So if you consider the E, there is no additional vertices with 0 degree, but the C in degree is updated with 2. 3 minus 2 is 3 minus 1, that is 2. So that is not 0. And if you consider this E, right? So after that the Q has D and G. Now again you take the G. If you take the G and remove these two, whenever you remove these two, this is the G, and you remove these two, the in degree of A is 0 and in degree of F is also 0. Previously 2. Whenever you consider the B, you remove this one. Now you consider the G and remove this one. In degree of F is 0. Now we add A and F into the Q. So finally the Q has F, A, D. So similarly you find the you take the D, just you D, and already in degree is 0. This is D. You consider this D. If you remove this one, C in degree value is 2 minus 1 is 1. C in degree value is 1. That is not it. So whenever you D, the Q has FA,